All right, good morning, gang. Today is a big day for us. We are going to have some fun learning a little bit more about power series. In particular today, I am going to teach you guys your first few tricks for finding a power series representation of a given function. So kind of remember the goal here towards the end of chapter 11 is God hands you a function and you need to come up with a power series for that function. Power series are beautiful, they're easy to work with in a lot of ways, they're very easy to integrate, differentiate, take limits of, all that good shit. I'll show you that next week. For now, our goal is just someone gives you a function, you give them a power series. That, and of course the stuff we did last time, which is just finding the interval and radius of convergence for a power series. I'm not going to do any more direct IOC or ROC calculations today. If you want to see more of that, or if you want to spend some more time on that, I invite you to go watch the video from last time. We did a bunch of those ratio test calculations, and all of the other ones go the same way. You run the ratio test, you check the endpoints, you get your IOC. I want to talk today a little bit more abstractly about the interval and radius of convergence.
I had a question really quickly.
This video, by the way, is a great video. If you guys are curious about Maxwell's equations, really recommend this 3 blue 1 brown video. Okay, yeah, Ayushi, what's up?
Is there any way we could schedule a office hour on Sunday by any chance?
Maybe. If you want to schedule an office hour with me outside of our normal time, just send me a Canvas message. And I'd recommend including like 2 or 3 different times that could work for you, because depending on my schedule, I may or may not be available during the time you want.
Okay,
Also,
over
the weekend. Yeah, we could find one.
Also for the homework, for the ROC and the IOC, you generally just use ratio tests, right?
Yes, you'll use the ratio test, and then you need to check the endpoints. So the ratio test will tell you what the endpoints of the IOC are, like -3 to 7. And then you'll need to check the 2 endpoints individually to know whether to use a bracket or a paren.
Okay, perfect.
Okay, this looks like there's another comment or question here in chat. Let's address that. Do we have class next Wednesday? No, next Wednesday is Veterans Day, isn't it? The 11th of November. So there will be no class on Veterans Day. So today we're going to talk a little bit more about intervals of convergence, which is a topic from section 11.8. And we're also going to talk about representing functions as power series. Which is 11.9. Now the 11.9 material I'm splitting up. It's not all going to be done this week. So the easy parts of 11.9 will be done this week. The rest of 11.9 will be done next week, along with Taylor's theorem. Those things just go together better. So this is the kind of roadmap. And as mentioned, Alex, yeah, no class next Wednesday. Next Wednesday is Veterans Day. I may end up posting some kind of extra material for you guys to look at between Monday and Friday of next week, because I don't want us to just not think about math at all during that time. But we will have class on Monday and Friday at least. Right, so let's jump in. You may remember at the end of class last time, I worked an example that looked a little bit like number 29 here. I told you, a certain series, sigma, cn, 3 to the n, or whatever is convergent, and I ask you, what can you tell me about these other series? I want to go a little bit deeper in that direction, and in particular, I'm going to look at something like this, like number 30. But I'm going to ask slightly different questions than the questions they ask here, and then I'll use the answer to the questions I ask to answer these. So I'm going to try to give you a little bit of perspective on this. So let's say, suppose the power series sigma n from 0 to infinity, cn x to the n converges when x is equal to -3 and diverges when x is equal to 5. Two questions. What is the smallest possible interval of convergence, which remember we abbreviate IOC, and then kind of the obvious other question, what is the largest possible? IOC. And once you have these two questions answered, any questions like those in the book or in the homework are very easy to solve. So all of these kind of tricky questions about where a power series may or may not converge, given some other information like this, stems from good answers to these two questions. First, I want to make an observation. The center of this series is 0, right? X to the n is x minus 0 to the n. So my interval of convergence must be symmetric about 0. IOCs are symmetric about the center. All right, so the IOC here has to be like negative some number to some number. Has to be like negative r to r. What happens at the endpoints, I don't know. Included, excluded, bracket, paren, who knows? But because intervals of convergence are always symmetric about the center, we can be confident that the IOC is, whatever the endpoint is over here. If the endpoint is -10, then the endpoint over here is +10. Good so far? Everybody comfy remembering the terminology, the center, interval, radius of convergence, all that? Okay. If my series converges when x is equal to 3, that tells me something about the interval of convergence. What number must be in the interval of convergence?
-3.
Yeah, remember the interval of convergence is the set of all x values such that the series converges. If this series converges when you plug in x equals -3, then -3 must be in the IOC. All right, so let's come over here. Here's -3. What's the smallest possible radius of convergence? What's the worst case scenario? If this number is going to be in the interval of convergence, and the interval of convergence has to be centered here, then the worst case scenario is that it stops here and just happens to include that number. Does that make sense? In other words, the radius of convergence, the distance from the center to the endpoint, has to be at least 3. Which means on the other side, we have to go at least out to +3. And over here, again, thinking about the worst case scenario, the worst case scenario is I don't include +3. I go out that far, but I don't include it. So because -3 must be in the IOC, I have to be able to reach at least 3 units to the left and stay inside my IOC. That means I have to be able to reach at least 3 units to the right and stay in my IOC. But we've seen that the endpoints can do different things. So if I want to think about what's the smallest symmetric interval about 0 that includes -3, that means I have to be shrinking in symmetrically like this, and I got to stop here because I have to include -3. If I came in any further, then -3 wouldn't be in the IOC, but I know that -3 is in the IOC. And because of the symmetry, I can't come in any further on this side. My interval has to be symmetric about the center. So this is my worst case interval of convergence. This right here is the smallest possible interval of convergence for this series. It's the left closed, right open interval from -3 to 3. So here's the solution for part A. That's it. The smallest possible IOC is the left closed, right open interval from -3 to 3. For part B, I want to do the same sort of thing. Now I know here that 5 is, if you plug in x equals 5, the series diverges, which means 5 is not in the IOC. So again, I come back to my number line. My series is centered at 0. I know that if I walk out here to 5, this guy is not in my interval of convergence. So if you're trying to grow the largest possible IOC, starting at 0, growing out symmetrically, what's the biggest possible I could get to? Well, I have to stop here. If I go past this, then 5 would be in the IOC, but I know that it's not. So I learn here that R has to be less than or equal to 5. Can't be bigger than 5, because if
I
it
have a
was bigger than
question.
5, then 5 would be included in my IOC. Yeah, what's up?
So if 5 isn't in the, what is it, IOC,
Mhm.
then why would it be equal to? Because when x equals 5, this series diverges.
I could have an open paren there.
Okay.
Yeah, so that's a good question, right? And this is exactly the idea. I'm trying to find the largest possible IOC. And here, this is sort of the best case scenario. If the series diverges when we plug in x equals 5, that means 5 can't be in the IOC. But I want to grow this IOC as much as I possibly can, keeping it symmetric about 0, but not including 5. How do I do that? I grow it all the way out here, and then I just say, okay, this endpoint is not included. And again, since I'm trying to maximize the IOC, I'm asking what's the biggest it can be. I can include this one, but I can't include this one. So my largest possible IOC is the left closed, right open interval. That's just a coincidence that they both ended up left closed, right open. Oh, -5 to 5, like this.
if we're given that one side is like divergent, can we automatically assume that the other one like is within? We could use the bracket, or is that just for this example?
Yeah, no, cannot always assume that. Here again, the questions I'm trying to answer are like, what is the smallest possible and what is the largest possible IOC? But just because you converge at one side doesn't mean you automatically diverge at the other, or vice versa. So I'm just trying to ask, if I know that the series converges when x is -3, then what's the smallest possible IOC? Okay, well that means since I'm trying to keep as few numbers in the IOC as possible, I maximize that or minimize that IOC by kicking out the +3. And similarly here, because I'm trying to find the largest possible IOC, I know I'm allowed to go up to 5 units away from 0. And if I want to include as much as possible, that means I would include the -5 here. But there's no reason to assume that -5 would be in. This is just the largest possible IOC.
Thank you.
Of course, yeah, no, it's a really good question.
So, sorry, another question.
Oh, no,
So in the case where, like, say this series diverges at x equals -5, then x equals -5 would be your open parentheses and 5 would be your closed.
if I told you that the series diverges when x is -5 and you are trying to build the largest possible IOC, then yeah, you would flip the bracket and the paren here.
Okay.
Okay, so now let's return to the types of questions that the book asks after giving this setup, right? So the book gives you a setup exactly like this, and so does one of your homeworks. But then instead of asking these questions, they ask questions like this: what can be said of the convergence of the following series? So under these conditions, what can we say about the series, let's say sigma n from 0 to infinity of just Cn, sigma n from 0 to infinity 2 to the n Cn, sigma n from 0 to infinity Cn times 6 to the n. Okay. Who can help me out with this first guy? How is this series related to my original series? What's the relationship between this series and the power series with which I just did all that work?
Isn't it the first portion of the series? So.
Not quite. I mean, the series here goes to infinity, so it's got the same number of terms as the power series here. What it doesn't have is any x's, right?
Would that make x equal to 1?
Very good. This is my series with x equal to 1 plugged in. Now, what do we know about plugging x equals 1 into my series? Well, if I look at the smallest possible IOC, the worst case scenario, the worst case scenario is that the interval of convergence is -3 to 3, closed on the left, open on the right. 1 is right here. Even in the worst case scenario, 1 is inside the IOC. Therefore, this series must converge.
So how is it not a part of the second series? right there.
What do you mean by second series?
Like not second series, but the largest possible IOC.
It is. It
So
is. One
why
is
do-
also right here.
Okay, so it's in both.
Yes, no matter what's going on, one must be in the IOC, which means this series must converge. You really don't need to think about the largest possible IOC to answer this question, because if one is in the smallest IOC, then it's automatically in the largest IOC, right?
Yeah.
So if you're a part of the interval -3 to 3, you're automatically a part of the interval -5 to 5. The idea is, even in the worst possible scenario, where the IOC is as small as it could possibly be, one is still inside, which means when you plug in x equals 1, even if shit is as bad as it could possibly be, you're still going to get a convergent series when you plug in 1. This is as bad as shit could possibly be. The IOC is -3 to 3. Even if shit is as bad as it could possibly be, this interval still contains the number 1, which means that my series will always converge if you plug the number 1 in for x. And that is
Yep.
what you do to get this series. So this series must converge.
I thought B was like a divergence thing, but they're both convergence, I just realized.
Oh, I see. Yes. Yeah. No. So in both of these cases, we're talking about intervals of convergence. Yeah. All right. Did everybody follow that logic? This is tricky stuff. I won't pretend like it's not tricky. I put questions that test this concept on every one of my exam 3s. And it's usually one of the most missed questions. So I want to spend enough time here that we're really comfy with this. The idea is that up here at the outset, I wasn't given enough information to say exactly what the interval of convergence has to be. I was just given enough information to get some estimates on the interval of convergence. This guy is enough to tell me that in the worst case, the smallest IOC is -3 to 3. And this is enough to tell me that in the best case, the largest possible IOC is -5 to 5. And so I want to classify these series as convergent or divergent based on the x values that they have plugged in. If the x value that any one of these series has plugged in is inside the worst case IOC, then this series must converge. And if the x value that these series have plugged in is outside the best case IOC, then that series must diverge. What can we say about the second series here?
Would x be 2 to the n?
X here is just 2,
Oh,
because this has an x to the n, and this has a 2 to the n. So this is my series with x equals 2 plugged in. And again, just like how 1 is in the worst case IOC, 2 is also in the worst case IOC. Since x equals 2 must be in the IOC, this series also converges. And then this last guy, what does he have plugged in for x?
C.
Um,
C of n.
well, C and they all have
Oh,
C.
sorry, 6.
Yeah, 6, right? This is my series with x equals 6 plugged in. Is there any way for 6 to be in the interval of convergence?
No.
No, because the largest possible interval of convergence is this, and 6 ain't in there.
So it diverges?
Yeah, so since 6 is not possibly in the IOC, this series diverges. All right. I've got one more question for y'all. Whoops, sorry, I ended up splitting there. There we go. One more question. I'm going to move this up. Let's see. Yeah, I don't really have a lot of choices here. We'll do it like this. What can be said about sigma n from 0 to infinity -4 to the n Cn?
-4 would be your x, right?
Here x is -4.
And that's in the smallest possible IOC, but it's not the largest.
Other way
Or
around. It's in the largest,
Yeah.
actually
right?
the other
But
way.
it's not
Yeah.
in the smallest. So -4 is here and here. So what can we say?
Is it conditionally convergent? then?
Yeah, I would say that too.
Well, conditional convergence means something very specific. It means when you take the absolute value of the series, it doesn't converge, but it converges normally. So if you said that this is conditionally convergent, you would be saying that this is convergent, that we can say for sure this series converges.
But we don't know that for sure.
But if the IOC were -3 to 3, then this series would diverge, right?
Mhm.
Right?
And if the IOC were -5 to 5, then the series would converge. So we don't have enough information. Not enough information about the power series is known to say whether x equal -4 is in the IOC. If we're in the best possible case, that would be a convergent series. If we're in the worst possible case, that would be a divergent series. And we don't know which of those cases we're in. This is between the things that we have enough information to say. The same would be true of x equals 3 or x equals 5, right? Because in the worst case scenario, x equals 3 is not in the IOC. Actually, in the best case scenario, we could say, yeah, definitely diverges at x equals 5. Yeah. But these are the types of questions that I'd like you to spend the most time on per question. So I understand that all the calculation questions where I actually give you the series and say, find the IOC and ROC, those take some time and you should crunch those out and they're good. But they don't take a lot of thought, right? It's really just like algebra. It's just like turning the crank. You just do it. But these two questions, the questions like 29 and 30 from the textbook, both of which are in your homework, really do require some thought. And I want you to put the thought in there to make sure you really understand what's going on, because they're tricky. It's definitely possible to spam answers in WebAssign and move on. But if you do that, you won't learn anything. So take the time to like draw these pictures and really think about what's going on. It'll serve you well. Any questions on what we did here? The key fact to remember, the thing you're dead in the water without, is this. Intervals of convergence are always symmetric about the center. Got to remember that to get started on any question of this sort. So that's, I would say, if you remember that, then you can kind of follow your nose the rest of the way by drawing number lines and thinking about possible cases. But we got to remember that IOCs are always symmetric about the center. Here, the center happened to be 0, so we knew that our IOC would run from -r to r. If my series was centered at 1, then it would run from 1 minus r to 1 plus r. All right, that is enough grinding on intervals of convergence. What I want to talk about now is how to actually find power series. So I give you a function. How do you even start looking for a power series? This is section 11.9. Representing functions as power series. And today I'm just going to teach you one trick. It's called the geometric series trick. And it's real simple. It's just 1 over 1 minus r is sigma n from 0 to infinity r to the n. The convergence here is only when the absolute value of r is less than 1. But this is the important thing to remember. For all of the 11.9 problems that you have in this week's homework, this is literally what you use, this and nothing else. So remember the game here. The game here is I give you a function, you tell me the power series for that function. The simplest example to start with I could ask you to find a power series for the function 1 over 1 minus x. How could we use the geometric series trick to find a power series for this function? What could I plug in for r in the pink formula to get a series for this expression?
X.
Yeah. Here we'll just take r equal to x, and we get that 1 over 1 minus x is sigma n from 0 to infinity x to the n. The center here is 0. And the coefficients, the CNs, are all just 1. Right? This is like 1 times x to the n. So all the CNs are 1. We can make this a little bit more interesting. I could ask you to find a power series for the function f of x equals 1 over 1 minus 2x. What do you think we would do here? What could I use for r here?
Would it just be 2x, r equals
Yeah.
2x?
Yeah,
Because
just 2x, right? If I plug in 2x for r in this expression, then I get 1 over 1 minus 2x. Okay, let's do it. So we're just going to take r to be 2x. And then I get 1 over 1 minus 2x is sigma n from 0 to infinity parentheses 2x to the n. And this I should clean up a little bit because I can't tell really what the center is and I can't tell really what the coefficients are. But 2x to the nth power is the same as 2 to the n times x to the n. And now I can see the center. X to the n, that's x minus 0 to the n, so the center is 0. And the cn's here are 2 to the n. So the center again is 0, and the cn's here are 2 to the n. This business of finding the cn's, finding the coefficients, you will see in the next chapter, or sorry, the next section, 1110, is pretty important. It's sort of the whole game. Because these series are all like cn times x minus a to the n. So once you know these two things, you can write down the series. For now, we're going the other way. You find the series, then tell me the center and the cn's. I have a couple other examples like this that I want to look at that are fairly straightforward. All of the first few examples here will be centered at 0. What about this? 1 over 1 plus x. Well, that doesn't look like 1 over 1 minus something, does it? Can I make it look like that?
Can you talk about like a negative?
Yeah. What if I write this as 1 over 1 minus negative x? That works, doesn't it? That's the same as 1 over 1 plus x, but now it's in that form, 1 over 1 minus something. So here I would take r to be negative x. And we see that 1 over 1 plus x is the same as sigma n from 0 to infinity, negative x to the n. And again, we want to do a little bit of algebra. That's sigma n from 0 to infinity, negative 1 to the n, x to the n. So here the center is again 0. And the cn's this time are negative 1 to the n. Questions on these first three examples? The next example I want to play with here, same business, find a power series for f of x equals, let's do 1 over x minus 3. This also doesn't look like 1 over 1 minus something. So again, here we need to use some clever algebra to rewrite this and as a 1 over 1 minus something. And my first step is going to be to say 1 over x minus 3 is the same as 1 over negative 3 minus x. I'm using this rule, that a minus b is the same as negative b minus a. If you distribute this negative, you'll see, okay, well, that's negative b plus a. That is the same as a minus b. So I'm force factoring out a negative. And then from there, I need to make this piece a 1, right? So this is negative 1 over 3 minus x. That's where we are right now. Now, if I can make that 3 a 1, I'm going to be happy. Then I'll have 1 over 1 minus something. So I'll force factor out a 3. And I'll have negative 1 over 3 times 1 minus x over 3.
And at that point, the 1/3 would just be a coefficient. So
Right, the 1/3 is going to pop out. I'll have a negative 1/3 times 1 over 1 minus x over 3 like this. So what am I going to take for r here?
X over 3.
1/3.
Good, yeah. I've got 1 over 1 minus x over 3. So I'll take r to be x over 3. I'm going to continue this on another page so I don't get too cluttered here. Let's do it like this. So what we'll see then is that 1 over x minus 3, my function, is equal to, I've got the negative 1/3, and then this piece I can write as a geometric series using r equals x over 3. So that would be the sum from 0 to infinity, x over 3 to the n. And we can clean this up quite a bit too. That's negative 1/3 sigma n from 0 to infinity, x to the n over 3 to the n. And then move down here. That's negative 1/3 sigma n from 0 to infinity, 1/3 to the n times x to the n, right? This 3 to the n downstairs is the same as 1/3 to the n. And then I can bring the 1/3, this guy, into the series. He doesn't have any ends, so he can come and go from the series as he chooses. This is a constant multiple. Remember, the rules for the sigma operator are the same as for an integral. The constants can come in and out. So this will be sigma n from 0 to infinity, negative 1/3 times 1/3 to the n times x to the n. And this can be cleaned up as well. That's sigma n from 0 to infinity, negative 1 times 1/3 to the n plus 1 times x to the n. The negative 1 is the negative. 1/3 times 1/3 to the n is 1/3 to the n plus 1, and x to the n is just x to the n. So the center is still a equals 0, and the CNs here are negative 1/3 to the n plus 1. Or you could say negative 1 times 1/3 to the n plus 1. Either one is fine. I like writing it like this because it makes clear who's getting the power and who isn't. The negative 1 is not getting the power, but the 1/3 is. Cool stuff, right? So this is the power series representation for this function. And if I graph the partial sums of this, just like we were doing on Wednesday, and I graph this, you would see the partial sums for this getting closer and closer and closer to this graph the more and more terms I use. I am going to do that with a different series a little bit later, but not right now. Right now, I'm just concerned about coming up with this series. So are there any questions about the steps that led us to getting this series or writing the center and Cn down? Okay. I've got one more kind of little example like this to play with, and I want to do one that's centered somewhere else. So let's find a power series. And here I'm going to specify the center. It's centered at a equals 1 for f of x equals 1 over 2 minus x. So remember, a series centered at 1 should have the following shape. It should look like sigma n from 0 to infinity Cn times x minus 1 to the n. So I'm looking for something that looks like this. The algebra trick here is to rewrite the bottom like that. Again, if you distribute this negative, you'll see that this is 1 minus x plus 1, which is the same as 2 minus x. So here I would take r to just be x minus 1. And you see right away that this is sigma n from 0 to infinity x minus 1 to the n. Sneaky, right? I could have done the same thing for this that I did to this and get a series centered at 0. But because I wanted a series centered at 1, I made sure to have an x minus 1 here instead of just an x over 2 or whatever. So here the center, as required, is a equals 1, and the CNs are all just 1. I don't think any of your homework specifies a center. I don't think any of the homework problems tell you you have to be centered at this place or that place that I gave you this week. But some of the homework problems that you'll see next week will specify a particular center. So you might want to hold on to this example, remember where it is, so you can look back at it. This is a pretty sneaky trick. I like this trick. And there are some problems where this will kind of save your bacon, where things are much, much easier when you do them this way. There's one other thing I want to talk about before we leave this land of relatively simple examples, and that's partial fractions. Remember, if I give you an arbitrary rational function, that is like a ratio of two polynomials, a fraction where the top and bottom are polynomials, and you factor the bottom, you can write any rational function as a sum of things that look like this, right? Like maybe with a different constant upstairs, but stuff that looks like constant over x minus constant. What that means is I could give you any rational function, like 1 over x squared minus 9. You factor the bottom, do some PFD. Then you could write a power series for each of those pieces, which means, in theory, you guys can now write power series for any rational function. And that's a big fucking deal because the rational functions are a huge family of functions. To me, that's very exciting. I think that's exciting no matter how you look at it. But some of those problems will take a bit of work. Now, there are a few in here. I think I maybe assigned one of them Might not have assigned it this week, but if you look in the homework for a problem looking like these. I don't know if I hit you with these this week yet or not, but you do some partial fractions, and then each of the pieces, you'll have a power series that looks like this. And you just put the two power series together. All right. The other thing that can happen when you run partial fractions, not every denominator factors into simple linear factors, right? We saw that back on exam 1 when we were talking about using partial fractions to do integrals. Sometimes you end up with irreducible quadratic factors in the denominator. So how do you find a power series? For a function like that, where instead of having like x minus 3 or x plus 5, downstairs you have like 1 plus x squared, some irreducible quadratic. How could I use the geometric series trick on this?
PFD.
Well, 1 plus x squared doesn't factor though, that's the thing. Yeah, if this was like 1 minus x squared, then I could factor and do PFD. But if you run PFD on this, you just get this back because the bottom doesn't factor.
Oh, I thought that said minus, sorry.
No worries, no worries. Yeah, if that was a minus, that would be exactly the right thing to do. But since that isn't a minus and I can't factor it, we're going to have to do something else. My goal is still to write this as 1 divided by 1 minus something. So how can I change 1 plus x squared into 1 minus something? What about this? The square is not outside the parentheses, the square is inside, right? So this really is the same as 1 plus x squared. This is 1 minus the negative of x squared. So here I could take r to be negative x squared. And we'll see that 1 over 1 plus x squared is the same as sigma n from 0 to infinity, negative x squared to the n. So I think the algebra trick here isn't anything too mind-blowing. If I gave you 1 over 1 plus x, you would write it as 1 over 1 minus negative x in the same way. We actually did that on the previous page, right? So here the only difference is it's an x squared. If I clean this series up, it looks like sigma n from 0 to infinity, negative 1 to the n times x squared to the n. But that's just x to the 2n. I want to do the same thing I did in all these other problems where I tell you what the center is and what the coefficients are. I'm going to do that, and you're not going to believe me at first. The center here is still 0. But the CNs actually follow a pretty complicated formula that I'm going to take some time to justify for you. So the center being 0 isn't too hard to see. X squared, or x to the 2n is x minus 0 to the 2n. But why would the CNs look like this? Why aren't they just negative 1 to the n? And what I have here is a negative 1 to the n. But it's the 2n up here that's fucking things up. Cn, remember, is the coefficient of x to the n. So let me write out the first few terms of this series. When n is 0, we get 1. When n is 1, we get minus x squared. When n is 2, we get plus x to the 4, and then minus x to the 6, plus x to the 8, and so on. There are no odd powers of x in here, are there? Well, there are. It's just that their coefficients are all 0. This is 1 plus 0x minus 1x squared plus 0x cubed plus 1x to the 4 plus 0x to the 5 minus 1x to the 6 plus 0x to the 7 plus 1x to the 8, and so on. So C0 is 1. C1 is 0. C2 is negative 1. C3 is 0. C4 is positive 1. C5 is 0. C6 is negative 1. C7 is 0. And C8 is positive 1. So all of the odds, C1, C3, C5, that looks like a 3, doesn't it? C5, those are all 0. All the odds are 0. And then if you pay attention to the evens, here k is 0, here k is 1, here k is 2, here k is 3, here k is 4. This really is negative 1 to the k. Negative 1 to the 0 is 1. Negative 1 to the 1 is negative 1. Negative 1 to the 2 is 1. Negative 1 to the 3 is negative 1. Negative 1 to the 4 is 1. So the formula I gave you here for the CNs is actually correct. It's a weird formula. And for this week's homework, and even most of next week's homework, this sort of thing won't matter too much. What really does matter is that you can get to this, right? That you can give me the power series representation, that you're able to arrive at 1 over 1 plus x squared equals this series. As long as you can do that, I'm happy. But if you're able to understand this, it will be very helpful when we talk about Taylor's formula, especially the formulas for sine and cosine. I want to do one more. This next one, we're not going to cook it up from scratch. I'm going to call the function g of x this time. Let's go for x over 1 plus x squared. Does anybody see a nice relationship between the function g of x here and the function f of x that we just found a series for? I know I just dumped a lot on you with this, so I'm going to give you a second but I want answers to this question. What's the relationship between this function and this function?
They're the same, just the bottom one is increased to is multiplied by x.
Yeah, g of x is x times 1 over 1 plus x squared. And I know a series for 1 over 1 plus x squared. X times 1 over 1 plus x squared is x times the series for 1 over 1 plus x squared, which is this. So once you start developing a library of series that you know well, you can get series for related functions by multiplying, dividing, shoving things around. Remember the constant from that early example where we had a negative 1/3 out here that I was able to push into the series? I was able to push the negative 1/3 into the series because it doesn't have any ends. As far as the series is concerned, negative 1/3 there was a constant. Well, as far as the series here is concerned, x is a constant. X is the variable of the function g, sure. But as far as the series is concerned, the series only cares about ends. So this sumbitch can be pushed inside. Just like the negative 1/3 from the previous example. And now everything in here is being multiplied. X times x to the 2n is x to the 2n plus 1. So here's your series for g of x. Boom, done. Didn't have to do any fresh raw calculation. I just used the series that I knew for this piece and multiplied by x. Now just for fun, because the last thing I want to do here is play around in Desmos a little bit, I'm going to write out the first few terms of this series. I'm not going to calculate the CNs here. It's a similar sort of thing as the last guy. But when n is 0 here, I get x, and then minus x cubed, and then plus x to the 5th, and then minus x to the 7th, plus x to the 9th, minus x to the 11th, plus, and so on. So just like this guy can be written out in long form like that, this guy can be written out in long form like that. Just expanding the sum. Just saying what this capital sigma thing really means. I'm going to give you a second to write, and then I'm going to flip over to Desmos. So I'll count to 10 or something here. Let me know if you need more time after that. All right, we ready for a little Desmos fun? Here we go. Again, this video, awesome, really good. 3 Blue 1 Brown in general, if you want to understand math concepts, awesome channel. Really recommend it. And a lot of people struggle with Maxwell's equations, so I can't recommend this enough. It's the right way to think about the Calc 3 concepts that are required for Maxwell's equations. But what we're doing is this. Let's begin with 1 over 1 plus x squared. Here it is. This is this graph. It's a famous graph. It's the derivative of the inverse tangent function. You know that, of course. But what we've done is find a power series for it, right? The power series that we found for this guy was 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 minus x to the 10 plus x to the 12 minus x to the 14 plus x to the 16 minus x to the 18 plus x to the 20 minus x to the 22 plus x to the 24 minus x to the 26. We can keep going. Based on this picture, anyone want to guess what the interval of convergence for this power series is? Where is this series doing a good job of sticking close to the original function?
-1 to 1.
Beautiful, right? Like 2, way the fuck out here, this thing is nowhere near the value of the power series. But if you stay between -1 and 1, my blue series does a good job of staying close to the red. The endpoints. Do you think the power series here is the closed interval from -1 to 1 or the open interval from -1 to 1? Does it appear to be doing a good job at -1 and 1? Well, look at this gap. At -1, my series is down here at 0, but the actual function is up here at 1, or sorry, 1/2. So no, the IOC for this series is going to be the open interval from -1 to 1. All right. A little bit more fun. Whoop, too far. Do you guys see any symmetry in the graph of the red function? Is this an even function, an odd function? Neither. Not a terribly hard question. You guys know this. What sort of symmetry do you see in this graph, in the red graph?
Isn't it even since it's symmetric by the y?
Good. Yeah, this function is symmetric about the y-axis, which means it's an even function. What do you notice about the terms of the blue series? What sort of powers of x are showing up?
Even powers.
Just even powers. Huh. So this even function has a power series, and the terms of that power series are all even. Have you ever wondered why we call even functions even? This is why. This is precisely why. Because the power series expansion for an even function contains only even powers of x. All right. So that's not a coincidence. This is always true. A power series that contains only even powers of x will always be a series for an even function. And the converse is true as well. If you have an even function, its power series will only contain even terms. All right. I'm going to play the same game, but with the second guy. Here's the graph of 1 over, or x over 1 plus x squared. If I delete the domain restriction, it looks like this. The power series that we came up with for this was x minus x cubed plus x to the 5 minus x to the 7 plus x to the 9 minus x to the 11 plus x to the 13 minus x to the 15 plus x to the 17 minus x to the 19 plus x to the 21 minus x to the 23 plus x to the 25 and so on. Let's do one more. Minus x to the 27. All right. Comparing the red and the blue, what do you think the interval of convergence is for this power series, whose 27th partial sum is graphed here in blue?
-1 to 1.
Good. Also -1 to 1. This blue series is doing a really good job of sticking on the red graph as long as we stay between -1 and 1. And again, at the end point here, at -1, we're kind of losing the function, right? The red goes down here, but the blue goes up here. And at the right endpoint, the red goes up here, but the blue goes down here. So probably it's the open interval from -1 to 1, just like the last example. And just like the last example, the red function has some symmetry. The symmetry exhibited here is origin symmetry, right? We're symmetric about the point 0, 0. You take any point over here, reflect it through the origin, you get another point on the graph. So this x over 1 plus x squared is an odd function. And you notice that the power series expansion has only odd terms. This leads us to a neat theorem. Odd functions will have only odd powers of x in their power series representations. And even functions will have only even powers of x. In their power series representations. So this is a cool fact. A function is odd if and only if its power series contains only odd terms. And a function is even if and only if its power series contains just even terms. Cool shit. One last thing before I let you go. All right, I know we're just about at the end of class, and what I'm about to show you is not relevant to this week's homework. It's only relevant to next week's homework. So if you gotta bounce, you gotta bounce. But I encourage you to stick around for just a few more seconds. This is a tasty morsel. Remember the power series, not power series, but the series from exam 2, sigma n from 0 to infinity, -1 to the n over 2n plus 1. This is the alternating series I gave you, and I asked you to run AST, show the series converges, and also tell me how many terms I need to approximate the value of the series with error less than 1/100, error less than 0.01. I claim that this thing is equal to pi over 4. A few people have come to me in office hours to review their tests, and after we went through this problem, I actually calculated the partial sum necessary. I think it was the 5th partial sum. And we were able to see that, I know it wasn't, it was like the 49th partial sum. We were able to see that the 49th partial sum gives a decimal, which is very similar to the decimal for pi over 4. I claim that these are exactly equal, that the value of this infinite series is pi over 4. You want to see how I get it? We start with the series we just worked with, 1 over 1 plus x squared, which is 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 minus, and so on. And you integrate on both sides. If you integrate 1, you get x. If you integrate x squared, you get x cubed over 3. If you integrate x to the 4, you get x to the 5 over 5. If you integrate x to the 6, you get x to the 7 over 7. If you integrate x to the 8, you get x to the 9 over 9. On the other hand, the integral of 1 over 1 plus x squared, that's the inverse tangent of x. And if I put this back into sigma notation, that's the sum from 0 to infinity, negative 1 to the n over 2n plus 1 times x to the 2n plus 1. All right, when n is 0, you get negative 1 to the 0 divided by 1 times x to the 1, that's x. When n is 1, you get negative 1 to the 1 divided by 2 times 1 plus 1, that's negative 1/3 times x cubed. This works, which means that the inverse tangent of 1 is what you get by plugging x equals 1 in over here. But the inverse tangent of 1, that's pi over 4. Pretty cool stuff, right? So that's our tasty morsel for the day. After you get good at finding power series, you'll be able to sum lots of other series by plugging in particular values for x and recognizing them as outputs from that function. So once I have this power series for the inverse tangent of x, I can plug in whatever x value I want, as long as it comes from the interval of convergence, and get a true statement. If you plug in x equals 1, the series becomes that series from the test. And on the other hand, when you plug in x equals 1, you get the inverse tangent of 1, which is pi over 4. So the series from the test is equal to pi over 4. Fun fact, back in the day, if you needed to calculate pi, you did it like this. So say you want pi accurate to 50 decimal places. Well, you would use the estimation theorem for alternating series to guarantee you get the value of this series correct to 50 decimal places, then multiply by 4. There are, of course, a lot of other series that you could use for this. Think about, other values you could plug in for x here. You get other things that involve pi. And there are totally different series besides the arctangent series you could use, like sine, cosine, other stuff. But this is how your calculator calculates pi. When you hit the pi button on your TI-83, it's doing this. It's taking a large partial sum here and then multiplying by 4. And that is the number it returns for pi. So this is how you would calculate pi on a desert island, or if you were trying to build a bridge from scratch and you had no technology. All of those situations where you need the important natural constants, they can be gotten as specific values of power series. I think this is beautiful stuff, and I'm really excited to be sharing it with you guys. Again, for now, you don't need this. We will be doing this sort of stuff next week, specifically integration and differentiation of power series. This step is a big deal. But for now, I want you guys to focus just on the problems that I gave you in the homework. So like this sort of thing. I give you a function, you find me a power series. That is the main task for this week. If you get stuck on any of that stuff, of course, you can bring it by office hours or send me an email. I will be working over the weekend on getting your tests graded. I'll get those back to you as soon as I can. Any questions for me before we head out?
Will you be having your office hours today?
Today, 3:30 to 4:30. Oh no, today's Friday, isn't it? Yeah, so today is going to be, I think 1 to 2. Friday,
I think it's 2 to 3.
2 to 3, yeah.
Yeah, okay.
All right, anything else, gang? Okay, then dive into that homework. Make sure you're working hard on it. And I will see you guys on Monday, if not in office hours.